All right, so I guess again, before we begin, if anyone needs to submit their homework 5 part 2s, you can go ahead and do that. Um, and homework 6 is posted on Blackboard. I think we'll try to get to this handout on chapter 3. There's a couple of questions from chapter 3 on that homework, so hopefully we should be able to cover that today. We do still have this topic from last time that we were covering, time-dependent motion, and another topic on objectivity. These are not really given in your book in too much detail, but I think are important concepts to understand. So we'll cover them sort of in a cursory way. There's a lot of depth to these topics. We can't really go into them in a lot of detail, but at least you should be aware of what the concepts are. So just to quickly recap, we were looking at this time-dependent motion where a body is deforming, obviously with time. We describe that in two different ways using two different but equivalent ways. Lagrangian description, which is given in terms of the original undeformed coordinates, and Eulerian description, which is given in terms of the spatial coordinates x. And I hope the distinction between these two things is clear to you now. So last time we did go through these definitions of acceleration and velocity, and we looked at this example of a uniform expansion in all three dimensions, but that an expansion where the rate of expansion is a function of time. And we came up with expressions for velocity and acceleration that matched with each other. I also talked about this material time derivatives, which, if you remember, we said you go and fix yourself to a point in space, and the material is flowing through that space. So in order to figure out what would be the rate of change of some quantity, say density for some scalar quantity at that point, you would need to take the partial derivative with respect to time and add a convective term to that to understand how the quantities related to a particular material point are changing. We know how we can measure how quantities like density at a point in space are changing, but that change in time is not related to a particular material point. So this material time derivative was something that allowed us to do that. So continuing with that, some more definitions of time-dependent quantities really here. In the static case, we came up with this F, which was the deformation gradient going from the undeformed configuration to the deformed configuration. When we have time dependence, we can measure the rate of change of F. So this single dot up there means d over dt. So d over dt of F can be written as if the deformation is smooth in time, then you can change the order of the derivatives, and you basically are taking the gradient of the velocity. So dv dz, where z is the undeformed coordinates, that's simply f dot. Okay. C dot in the similar way, just d over dt of the definition of C, and we apply the product rule to get f dot transpose times f plus f transpose times f dot, and E dot is just half of C dot minus I dot. There is no I dot because I is constant. And similarly on the spatial side, we have these gradients of time which are important physical quantities. So f dot, the same thing that we had on the Lagrangian side, can be expressed as partial v partial x. This was the velocity gradient, if you remember from last time. And applying the chain rule, we can write it as partial x partial z. So L times f. F dot is simply L times f, which means that if I post multiply both sides by f inverse, then this becomes L is equal to f dot f inverse. This is a very fundamental relationship that that people use to describe time-dependent motion using the velocity gradient. Now this L need not be symmetric. So in order for some constitutive properties, meaning material properties, to be defined, people often come up with the symmetric part of that tensor. You remember any tensor can be broken up into its symmetric part and anti-symmetric part, right? So that's what we are doing here. We are defining the symmetric part of L as this tensor D, which is the rate of deformation tensor, and the skew symmetric part is the spin tensor, half of L minus L transpose and half of. So if you add these two, D plus W, you get back L. You can verify that easily. A little bit of algebra here, but without going to that algebra, I'll make a couple of quick comments. Maybe some of you have looked at the physical interpretation of these D and W tensors. But if we just go by the definition of D, it is half of L plus L transpose. After plugging in the polar decomposition of F is equal to RU, and again, do the product rule and so on. If you expand it after a bunch of algebra, you see that D can be written as half of R times some rate of stretch times R transpose. Okay. So D does capture the stretching part of the time-dependent deformation, just like U and V tensors were doing. Whereas W is a spin tensor, and some people think of it as a rigid body rotation part of that deformation. However, if you expand W, you can see that it has R dot R transpose plus something that is related to stretch as well. So spin tensor is not a pure rigid body, does not capture only the pure rigid body rotation part, but it also captures some stretching part. So a little bit more of this physical interpretation, I'll do that with a rigid body rotation example. But before I do that, I'll introduce something else called an axial vector of a skew symmetric tensor. So if you have any skew symmetric tensor, W, that skew symmetric tensor can be written as, well, will have zeros on the diagonals, and the opposite or the off diagonal components of that tensor will be negative of each other. So if you take that tensor W acting on an arbitrary vector, that vector can be represented as this tensor acting on a vector will give you a vector. This resulting vector can be expressed as a vector W, which is actually an angular velocity, I'll show you in a bit, cross product with this vector U. So in effect, the action of this skew symmetric tensor on U can be represented with a cross product of this angular velocity with the same vector U. And there is a little bit of a kind of a pseudo proof here of how to derive the axial vector. But what you really should be able to see is that the components of this angular velocity vector W are these three: W32, W13, and W21. So W32 is right here, W13 is right here, and W21 are right here. So these and then this gives me this W23, W13, and W21. So if you take any skew symmetric tensor, if you pick out these three components in that order, then that would correspond to the axial vector omega of corresponding to this skew symmetric tensor. And this axial vector omega cross product with any arbitrary vector U would be the same as taking the tensor acting on U. And this interpretation helps us with another kind of concept that hopefully you've all seen before. I know you've all seen before back in probably your sophomore year. Let's say if I have a rigid body that's rotating about some axis. Okay, so this green line here, that's, let's say, the instantaneous axis of rotation. I have my rigid body in the black configuration. rotated rigidly to this blue configuration. And since it's a rigid body motion, the stretch tensor U would be identity. Therefore, the deformation gradient F would be simply the rotation tensor. There is no deformation, so D is 0. And L would be the velocity gradient immediately available from R dot R transpose. So only in a rigid body motion, that term goes away. R dot R transpose is what W is capturing. Hopefully you've all seen this relationship that when we have this type of a rigid body rotation, you can express the relationship between 2 points A and B on the body, where the velocity of A, velocity of B it can be correlated with the angular velocity omega times the position vector, relative position of B versus A, right? This thing here, xB minus xa, that's the relative position of B with respect to A. So the relative velocity of B with respect to A is given by omega cross R. Does that ring any bells? If I have a rigid body rotation, 2 points on the body, the relative velocity of point B with respect to A, which is this guy, is equal to omega cross R, where R is the relative position of B with respect to A. And that's exactly what this spin tensor does. In case of a rigid body motion, dV can be expressed as omega acting on dx. So if you have the same dx here, then that can be expressed as omega cross dx using the axial vector. So, so this is just sort of a helpful interpretation of what this spin tensor does. I've not really talked much about the deformation tensor, D, but hopefully this should help you correlate it with something that you know from rigid body dynamics. I'll quickly do an example of a time-dependent map here. So here I have this map of this expression given as 1 plus alpha, some function of time. I'll tell you what that function of time is. And the vector r, where that vector r is z1 e1 plus z2 e2. So very similar to our cylindrical definition, cylindrical coordinates definition of r. And another function of time times z3. So what this map is doing is it deforms the body in the radial direction using one factor. That factor is this one up here. And it deforms the body in the vertical direction, z3, in the e3 direction, using a different factor. And I've written sort of the explicit expression out here. I'm saying that the function f, this function, is a ramp function which goes up to its maximum value at 1. So initially it's 0. That gives me this profile. And after time 1, what I get is that the value of this function is 1. So I get 1 plus alpha times 1. Therefore, the lateral dimensions, E2 and E1 and E2 dimensions increase, which is what this blue configuration is showing. So the original was black, and after time 1, we get this deformed blue configuration. And you will notice that in addition to that, we have the height of that changing. So it drops down by beta, and it expands by alpha is what's happening. This is what the map is. Clearly, this derivative of f would be discontinuous function, right? And for this particular map, I've calculated off your deformation gradient as well, which is simply the time derivative of this map with respect to z1, z2, z3. So let's quickly verify. Time derivative of the first term with respect to z1 gives me that factor, which is up here. There is no z2, so we get 0. With respect to z3, there is this guy. So alpha z1 times derivative or time derivative of f. So again, just applying chain rule, and then 1 over v0 is the factor up here. If we do that for the second and third rows, we get this as the time-dependent deformation gradient. Okay, and I'll show you a couple of animations here of how to visualize these things. But essentially, what we are doing is plotting determinant of f. What is determinant of f, by the way? What is the physical significance of determinant of f? Local volume changes. Determinant of f is proportional to local volume changes, right? So let me go ahead and start this. So that's just plotting determinant of f, and so it's kind of like a bag of grain, a square or a cubic rectangular bag of grain that has been suddenly left loose and it falls into this container. That's sort of what this is trying to mimic. So you can take f dot by simply taking the time derivative of each and every term in here, and you can verify that that's what you get with f dot. The spatial or the velocity gradient, the spatial velocity gradient L is partial v partial x, or just as we saw on the previous page, it is f dot times f inverse, which is here, f dot f inverse. So L can be computed. We already know f. We already know f dot. The matrix multiplication of those components gives me the tensor L. You can calculate D, which is symmetric part of L, and calculate W, the spin tensor, anti-symmetric part of L, and you can plot some of these quantities. I'll post this code on Blackboard, and you can plot different things. One is for determinant of F, which is what I just plotted. 2 is for trace of L, which happens to be trace of D in this case, and 3 is the norm of the spin tensor. So without going into too much physical interpretation of these quantities, this is just to kind of expose you to the fact that indeed all of these deformation processes are dynamic, and there are certain quantities of, just like for statics, for static deformations, we came up with F, C, E, these things. We have these corresponding tensor quantities in time-dependent deformation. And again, we are not going to go into too much detail about this. Any burning questions on this? Go ahead, Ila.
When we calculated the spin tensor,
Okay.
for the Q symmetric tensor W, in that part, I didn't get why did we first at all take those negative signs below that?
Here?
Yeah, those negative signs, and then why did we neglect them?
No, because we did not take negative signs here. So all I'm saying is that how do we do cross product? Cross product is E1, E2, E3 components of W. The components of W itself are the negatives of those, because W32 is the negative of W23, right? So this guy W32 is the negative of W23 because this is a skew symmetric tensor. That's what I meant here. Okay. Any other question? All right. So one last topic of very important topic in kinematics is called objectivity or frame indifference. Now, this topic is about the fact that when we conduct any physical experiment, okay, there might be multiple different observers observing that physical experiment, and all these observers must record the same process. That if two different observers are observing the same physical process, they should not come up with different conclusions, right? So this objectivity means that that we need to define our physical process using quantities that do not change when I change the observer. So let me first define something called a frame of reference. Now, a lot of people think that frame of reference just means my coordinate system, X, Y, Z, or something like that. It's not true. Frame of reference has got nothing to do with a coordinate system. A frame of reference is maybe for what you can imagine that to be as an observer, or if you have a video camera or something, just think of it as a video camera with depth perception, something like that. And here's an example of that. Let's say I have some physical process going on in this space shuttle. It's floating up there in space somewhere, and there are two observers. Each has their own frame of reference. One I'm calling F, and another one calling F star. They are both trying to record changes in length or changes in deformation of this body. So let's say this body is undergoing some physical process of deformation. They are both recording that process. The image, or the three-dimensional image that one frame of reference records, is from its own point of view. We see that body here. We also see that other frame of reference here, other observer here. But just to distinguish from a frame of reference from a coordinate system, you can easily imagine that for this observer, for the observer F, I can set up a coordinate system E1, E2, E3 in my own frame of reference. So let's say we are corresponding to frame of reference F. In our own frame of reference, I could have E1, E2, E3 as one set of coordinate systems. E1 prime, E2 prime, E3 prime is yet another different coordinate system. So within the same frame of reference, I do have multiple possibility of any number of multiple coordinate systems. The same thing from a different observer, they get a different picture, they record different vectors. So F, the observer F, records this vector that points from A to B as this vector, let's say some vector u. Similarly, this observer will record that same vector as u star. And in order for them to be able to talk to each other and communicate about the same vector, we need to have certain relationship between this u and u star. Okay. Now it's easily possible that we have this process going on, that space station, that process in the space station, that space station itself could be moving and rotating and so on. Both of these frames could be either circling or going with some linear velocity. So we need somehow to be able to relate these two vectors. So to get those relationships between these two vectors, we should realize that in one frame of reference, actually I'm showing you the other sort of the other frame of reference as well in this, but this is just so that you can relate it to something like a rigid body rotation. If I take my frame of reference, do a rigid body rotation to the point of view or to the frame of reference of the other observer, that is what this Q tensor captures. So for any coordinate system rigidly attached to one of the frames of reference, I can obtain the coordinate system attached to the other frame of reference using a rigid body rotation. That's what we are showing here as EI is equal to Q, a rigid body rotation of GI. Okay, so the basis vectors here, G1, G2, G3. If I take a rigid body rotation of those basis vectors to these corresponding E1, E2, E3 attached to F, that would be captured by this Q rotation tensor. And they both have their own time, so time is not really a problem. Usually, it's a scalar quantity. If it's just if you adjust time by some scalar alpha, then time of both these frames of reference can be matched. Orientations are matched with this Q rotation tensor, and position of a point X in terms of something that is given by the other frame of reference is as follows. So let's see. Let's say that I'm looking at some point B here. The position vector of that point B with respect to the frame of reference with respect to F is given by X. The position vector from that frame of reference is given as X star. If I try to correlate that, then I need the position vector of that point with respect to myself. That's I'm calling minus C, and therefore the position vector from F star to myself is C. All we need to do is to express X star. So if I go into this frame of reference, I have some vector X star. Okay, I have to do a rigid body rotation to that vector, and I think there's a easier way to explain this. Let's see. So X star minus C, which would be basically if I take this vector minus C, that's vector is right here from this point all the way to this point. If I add X star to that, then I'm adding this vector. Okay. Now that would be with respect to that vector would be with respect to the F star frame of reference, and to obtain the corresponding vector X in the F frame of reference, we'd have to do a rigid body rotation of that vector. But here's sort of the more important definition of what objectivity means. If I record if these two frames of references record the same vector u, okay, that vector u was pointing from A to B. That's the vector u. In this frame of reference, I get a vector u star. In this frame of reference, I get a vector u. And the relationship between those two vectors will be given by this rotation tensor. So if you take the vector u, do a rigid body rotation to F star observer, then you get u star. In the same way, do an inverse rigid body rotation of u star to get back u. For tensors, the relationship for objectivity is that if they both measure, let's say, deformation gradient, okay, there is both these frames measure deformation gradient for this body F. So that tensor can be transformed again between those two frames of references using that same rigid body rotation. But if you are given tensor T with respect to frame F, you would have to check this. You would have to obtain T star by doing T times Q transpose and pre-multiplying with Q. So again, I'm not going into the details of this derivation of what this objectivity means, but the idea really is that you have two different or multiple different frames of reference observing the same process. If I'm looking at a vector quantity from these two different frames of references, the condition for objectivity is given by this rotation transpose for frame F and Q for frame F star. They both have to be related that way. If there are quantities that are not related, if there are vector quantities measured by both of these frames of references that are not related by this relationship, they are not objective, because one frame of reference would say that, hey, my vector is u, and the other would say, well, no, that's not what I get if I do a rigid body rotation. A very simple example of that is velocity, something as basic as velocity. So you might say that, okay, in frame F, I'm going to measure the velocity of the point A. Okay? it's maybe moving in some direction. Frame F says my velocity v is just the rate of change of position of point A or of point B. Similarly, frame F star measures the same thing, rate of change of position of point A or of point B. That velocity v, which is rate of change of position, in the two coordinate systems, you can show that that velocity is not objective. The two frames of references will not, that the velocity vector does not transform using the simple relation of q times u is equal to u star. You can show that if I just take x star right here, c plus q transpose plus q times x. So c plus q times x, if I take the dot product of all of that, the dot time derivative applying the product rule to that, we get c dot plus q dot times x plus q acting on v. For it to be, for velocity to be objective, I should have gotten only this term, but I also get c dot, I get q dot plus x. So a basic thing like velocity is not objective. Similarly, acceleration. Acceleration is not objective. If you apply the definition straight away by taking time derivatives of the position, two time derivatives of this position. So in the same way, there are lots of other quantities that are both vector and tensor quantities that are not objective, but we need to describe physical processes in terms of objective quantities. So what people did was to come up with certain rates of deformation that are objective. This d, the rate of deformation tensor that we talked about, that happens to be objective. There are lots of other rates, co-rotational rate or convected rate, and lots of different types of rates that people have come up with, that if you compute rate in that manner, then any two observers observing the same vector or the rate of change of that vector will come up with two quantities that do correlate with that Q tensor. So, and this is all important when, for example, you are trying to correlate stress with strain. If two different observers measure strains and stresses, the relationship between stress and strain also has to be objective. Material does not depend upon who is observing that material, right? So material behavior is independent of the observer. So anyway, I think this is a topic which is again still actually an active area of research where people try to understand it better, but it's something that you need to be aware of. Question?
Shouldn't T should be equal to T star? Why
What do you mean?
The definition of all the things. Yes.
This T?
Time, both the times to be equal.
No, because, well, so let's, no, okay, so time is a scalar quantity, right? Time depends upon where your zero of that time is.
But you are taking daytime and time.
So, okay, in this frame of reference, maybe one example is, let's say we are in the US, there's somebody in Russia sitting out there, there's a time difference between them, right? They're both observing the same process, but their definition of time is basically shifted by some constant value. Okay, other questions? All right, so I think what we'll do is switch gears and start talking something more about much that is very, very has a great physical interpretation here. So what we've done till now is looked at a lot of mathematical preliminaries in chapter 1. We looked at how can we describe deformation in chapter 2 of kinematics? Kinematics that we just finished is pretty much only about how do you describe the deformation. If you have a map, you can calculate F, C, I, you can decompose it in R and U and whatnot. You can calculate changes in length, changes in area, changes in volume. All of those things are description of the deformation. If you're given the map, you can describe all that. Here, what we're going to try to do is to try to understand what keeps deformable bodies in equilibrium, what keeps and what causes them to move or to deform. Okay, so now we are going to get into trying to understand equilibrium of deformable bodies. So one quick thing here about equilibrium. Say this is a deformable body here, and if I fix it at one end, if I apply load at the other, it obviously deforms. And if you try to imagine two different parts of the body, something that we do in drawing free body diagrams, right? We don't actually cut the body, we imagine two different parts of the body. So if I imagine, let's say, the right half of this body, then the left half of the body is applying some forces to the right half also. This is my left hand, and I'm trying to show how it might be applying some forces on my right part of the body. So what kind of forces do you think are those? If I imagine two different parts of the bodies, there are atoms and molecules and some material structure on the left half and other set of atoms, molecules on the right half. They interact with each other with electromagnetic forces, really, or forces of bond, right? They are at minute atomic scales that we are talking about. That's what keeps a material together. Once those bonds break, or that material structure breaks at the atomic or the microscopic level, then we have fracture of a body. So those interactions that we are talking about are electromagnetic forces between atoms and molecules of that body. It's these types of forces that we are going to pretty much sort out all the local variations. So you can obviously imagine that if there are a bunch of molecules, they are interacting with another bunch of molecules. Those forces are not like a smooth continuum description, right? They are pairwise, or there are discrete set of forces that are acting between these quote-unquote particles. But in our discussion, we are going to neglect all of that small, minute scale variations. We are going to say when we imagine parts of this body, we are going to imagine them to be behaving as a continuum. Right? We know that there are atoms and molecules, discrete set of particles in there interacting with each other, but we are going to assume that the body is a continuum, and that's the way that they are going to interact with each other, where the forces that the left half, for example, applies on the right half will have to be interpreted as a distributed force over either some surface or some volume, some edge, or something like that. All right. So let's try to get back to the problem of structural mechanics that we had defined some time ago. Original problem that we wanted to solve was, given some structure, boundary conditions, loading, material properties, then I would like to find displacements, strains, and stresses in this body. Right? We did cover the kinematics part of that definition, which correlates displacements with strains. And now we are going to talk about the force part of that problem. And this last part here will be about material properties. And then that will allow us to completely define a problem. So let's try to understand how to determine whether a body will be in equilibrium or not. Now, early on in your undergraduate studies, you did a lot of these free body diagrams, right? That's how we determine whether a body is in equilibrium or not. So for example, if I have this body, given these set of boundary conditions, that loading, hopefully you can imagine that on the back face where the body is fixed, the wall is applying some forces to this back face. Maybe I'll draw that somehow. So there's the back face, which is all fixed against the wall. The wall is going to be applying forces onto this body, and in a free body diagram, we draw only what is external to that body, right? So these forces that the wall is applying are given in this manner. Maybe to sort of motivate that a little bit better, let's take a simple example. If I have a cantilever beam fixed at the left end, and I'm applying some distributed force P to the right end, can you tell me what the bending moment diagram, shear force diagram looks like for this? Okay, shear force diagram would basically be, well, first we calculate reactions. So P at the wall, and moment M, which would be equal to P times L, where let's say L is the length of that beam. Shear force diagram is go up to P, go across, constant shear force, drop down, and the bending moment diagram, of course, would be negative. So I should move this line up, and 0 at the tip, and up to PL here. But what do these things mean? Shear force and bending moment diagram. If I take a cross section, let's say somewhere here, I take a cross section somewhere here, I imagine two different parts of this beam, left and right. So I'll draw those as well. This is the left and the right halves. I have my external force P as a distributed force on the right hand. I have my reaction forces at the back face. That reaction force P at the back face is also a distributed force coming from the wall that is keeping the left end of the beam up, right? And in addition to that, I have this bending moment. That bending moment is the resultant of all of these distributed forces that look like this. So the top part is in tension and the bottom part is in compression. Do you agree? And the same thing at any cross section. This cross section right here, the magnitude of that moment becomes smaller, but again the top part is in tension and it matches equal and opposite to the other half. The bottom part is in compression, matches equal and opposite to the other half, and then we get that sort of distribution. Okay. So I think the important point here is, and actually I'm missing something here. There is P up here and there is P down here. So if you were to try to plot the actual distributed forces, let's say on the wrist, on this fixed end, the actual distributed forces on those fixed end would be a combination of the distributed forces due to shear and the distributed forces due to the moment. The distributed forces due to the moment, I drew it like this right here, like in a triangular manner. Can anybody tell me what are the distributed forces due to shear? What do they look like on a cross section?
A bunch of vectors going this way with this way.
with all the same length, or would be something else? So, okay, let me try to draw that. The distribution due to shear is actually quadratic, right? The distribution due to shear is the greatest shear is in the center of the in the center of the cross section, and the shear dissipates away from the cross section towards the end. That's what shear distribution looks like. And on top of that, we have this bending distribution. So if I move that a little bit and draw that bending distribution, so I'll have tension on the top half, and the amount of tension keeps on decreasing towards the neutral axis, and then I have compression in the bottom half, or the other way. So if I combine these two, these are not two independent set of distributed forces. The actual distribution on the rigid wall at the left is a vector sum of these two. Both of them just get summed, and what I get is something like this, where so I'm not sure if that's, so you kind of get this sort of a distribution of distributed forces on the left fixed end. And you can imagine that if you make a cut somewhere in the middle, yet once again you'd be combining a shear distribution together with a moment distribution to get these sort of distributed forces on a surface. Okay, so that surface that we are talking about, the cut surface, there are many different points on that surface. Depending upon where in that cross section you are, the resultant of the distributed force could be pointing in different directions. At the top of the cross section, there is zero shear and there is only tensile distributed forces. Right? So we get these arrows. We get these arrows on the top of the surface. In the middle of the cross section, there is zero distributed force due to the moment, but the maximum distributed force due to the shear. So the direction and the magnitude of that distributed force along the cross section varies. And that's what I've tried to capture in that figure that I've drawn here. Maybe not very well, but the fact is that when we draw a free body diagram, we are drawing all the external forces to that part of the body. And another important part of that is, no matter what part of that body you imagine, all of the forces will have to follow these three Newton's laws right here. First law says if the sum of forces is zero with respect to inertial frame of reference, then the body stays at rest or in that same constant motion. Second one says F is equal to ma if the forces are not equal. And the third one, which is the most important for free body diagrams, is to make sure that all forces occur in the universe as pairs, as equal and opposite pairs. So if I have body A applying some forces to body B has to be applying equal and opposite forces on body A, point-wise. Meaning, if I look at the cross section in these two cross sections, then this vector, for example, this distributed force vector coming from B is equal and opposite to this distributed force vector coming from A onto B. Okay, so in this way, you can draw the free body diagram of any object or any part of any object. And in order for equilibrium to hold, each and every part of that body must be in equilibrium. Therefore, for example, in your undergraduate studies, we used to say, well, sum of forces and sum of moments should be equal to zero for this body to be in equilibrium. But that's not only for the entire body, but you can do the free body diagram for any small part of that body and the sum of forces and moments have to be 0 for no matter what part of that body you choose. Then the body is in equilibrium. Okay. All right. So I think I'll have to stop here, and I'll come up. I'll continue this discussion on Wednesday.
Still trying to figure it out. So, is it okay to submit it on Wednesday? The other two parts are submitted.
Okay.
Question 1 and 2.
Okay. Yeah, I think the solution is up there, right?
Yes, solution. So, actually, because I had started doing it Chandra's way.